Hello, thanks for joining us today. We're going to be talking about lesson 6-1, the second fundamental theorem of calculus. In another video, we'll be addressing rate graphs. Let's get started. So the first thing I want to draw your attention to is something we covered in chapter 5, which is that because differentiation and anti-differentiation are inverse operations in some sense, that if we apply them in this order, they would cancel out and leave just the integrand. However, in 5-6, we introduced the idea of a definite integration. So we should try to see what happens here. And this is more or less the question the second fundamental theorem is designed to ask or answer. So, straightforward integration, 2t, integrating with respect to t will leave us with t squared, add 1 to the power, divide by the new power, minus 3t. And as I mentioned in the last lesson, in 5-6, what you want to remember is that we don't need a constant of integration when we're doing definite integration because they would cancel out. We'd have 1 for this upper bound at x, and 1 for this lower bound at 0, and constant minus a constant would just be 0. So we don't have to worry about that. But we do have to worry about plugging in the top, x squared minus 3x, and then we'll subtract and plug in the bottom, which is 0 squared minus 3 times 0. So what we get here is just x squared minus 3x, because this quantity is just 0. Okay, so if we're trying to differentiate this integral we just did, what I'm really talking about is differentiating the derivative I just got. So we're really talking about taking the derivative of this antiderivative, or net change, this definite integral. And what would I get if I carried out this differentiation? I would get 2x minus 3. So they prompt us with the question, do we notice anything yet? Well, what I might notice, and you should pause the video to maybe think about this first, if you haven't thought about it. What I might notice is that my integrand almost matches my answer. Here we had an exact match up at the top from lesson 5-4. Here we have an almost match, with the key difference being that we have replaced t with x. So let's try another example. This is working with an abstract function, f prime. The antiderivative of f prime, once you get good at calculus, should feel easier than any other antiderivative. F prime is the derivative of which function? F prime is the derivative of f. So the antiderivative of f prime is f. We're just going backwards. So that's f of t, and I'm evaluating that from 10 up until x. Plug in the top bound, minus plug in the lower bound, and we get an expression like that. And again, example 4 asks what would happen if I differentiated that which I just integrated. So to be clear, it's asking us to differentiate f of x minus f of 10. And what else would I get? Well, we're going to take the derivative of f of x, which would just be f prime. And then the derivative of f of 10. F of 10 is just some value. F of 10 is the y-coordinate on the graph of f when x equals 10. So we're taking the derivative of some constant number, which is 0. So we get f prime of x. That's my final answer, which again matches the integrand with just the variable replaced. Now quickly, I want to say again that the derivative of f of 10, this is something that happens on the AP test a lot, is not f prime of 10. Okay? And it all has to do with the order of operations here. This says plug in 10 and then take the derivative. This side is more like take the derivative of f of x and then evaluate that answer at x equals 10. So again, that order matters a lot more. That order gives us the slope of f at 10, whereas this gives me just the y value. And then I take the derivative of some y value, some number. So this side is always 0. This side could be any number. Okay? Just a quick aside. So that brings us to the second fundamental theorem of calculus. For any constant a, the derivative of the integral of just a function f would be f of x. Now again, I'm going to emphasize that it's very important that we have the derivative there. This doesn't change anything about having an integral. So make sure you only apply this theorem when you're taking the derivative of an integral. If that derivative sign wasn't there, you would not use this theorem. You would use all the techniques described in 5-4, 5-5, and 5-6. I'll also say that x, the top bound, is replacing right here, is replacing the t, and that the lower bound, because it was a constant, will just become 0, because we're taking the derivative of the antiderivative at 0. Okay? This is a more common use of this theorem. This will show up more frequently on the AP test. It's not that necessary, though, if you memorize the more complicated version we're about to do. The more complicated version will work in more situations. So here we go. I recommend you could try these out. I would take a second, try all 4 out. Once you're done, you can hit play. 3, 2, 1, fair warning. So this is f of t, because the antiderivative of f prime is still f of t, from 0 to x squared, which is f of x squared minus f of 0. Now we're going to take the derivative of that. The derivative of f of x squared would be f prime of x squared. I took the derivative of the outside, keeping the inside the same. This is the chain rule, times 2x, which is what we would have called a hook on back in chapter 3. Minus, and again, the derivative of f of 0 would just be 0. So we're talking about just getting my chain rule type answer, f prime of x squared times 2x. And again, this is outside. That's the input. X squared is the input, not x squared times 2x. You would take the derivative, plug in whatever that value is, and then multiply that value to the whole output. In this case, it's pretty much the same as the example above. F of t would be the antiderivative, evaluated from x cubed to 2x. So we're talking about f of 2x minus f of x cubed. And here we're taking the derivative of that. We're taking the derivative of this answer outside first. I'll change color. Outside first. Keep the inside the same. Multiply by the derivative of the inside. Minus outside first. Keep the inside the same. Multiply by the derivative of the inside. And there you go. Again, notice this is only the answer if I have the derivative on the outside. Notice the insides don't match. Notice there's no hook-ons over here. That's a really common mistake when you first get started with these problems. So, what changes do we notice? The main change I noticed is that if my bounds are complicated, well, what we needed to do, we needed the chain rule. Which is exactly what the next theorem will say. So the chain rule version is, again, if you have a derivative of an integral, we have v, the top bound is going to replace t, and we have v prime, and the lower bound is then going to replace t with u prime. Okay? This theorem works for the other theorem. This chain rule version replaces the other theorem. So if we're talking about the derivative of the integral from a to x of f of t, using this theorem, I would just have f of x times the derivative of x minus f of a times the derivative of a. Well, the derivative of x is just 1. The derivative of a constant, is just 0. So we get f of x minus 0, or just f of x. And this is exactly what we said 2 slides ago. We just get f of x. So this is the much more important theorem. If you memorize this theorem, you will be able to do all second fundamental theorem problems with ease, I hope. Here are 6 examples. I recommend you pause the video, try them out, and restart after you finished all 6. I'll be working on them in order. If you feel uncomfortable, you could unpause after each one, I suppose. 3, 2, 1, here I go. So, it said we could plug in the top bound. I'm going to write it right here. 2 times 0 minus 3, all times the derivative of the top bound. I guess I'll write this in orange. Minus, we would plug in the lower bound times the derivative of the lower bound, for a final answer of, so this holding 0, negative 2x minus 3. I'm not going to simplify more than that. You are welcome to. That would equal negative 2x plus 3. Careful with your distribution. This one's a more interesting example. We're going to plug in the upper bound first, the top bound first, times the derivative of the top bound, which is just 0. The derivative of 5 is 0, minus We're plugging in the lower bound times the derivative of 2, which is 0. 0 times this minus 0 times that, a final answer of 0. Conceptually, this should make sense. A definite integral without complicated function bounds, this represents the area under the curve, which is just some number. And if I take the derivative of that number, I should get 0. Okay, next. Plugging in the top bound, x cubed squared plus 2 times x cubed times the derivative of x cubed, which is 3x squared, minus, you would plug in -1 very carefully, with parentheses, I hope, all times the derivative of -1, which is 0. Again, a pattern you should be taking note of is that when we have a bound that is just a constant and I'm taking a derivative, it's all going to be 0 because the derivative of that constant will be 0. So what we're really getting here as a final answer, I would simplify x to the third squared, that's x to the sixth, plus 2x cubed times 3x squared. If you are sharp with your algebra, you should be able to write that down in one go, but I'm just trying to be clear, this is also an acceptable final answer. We don't want to lose points just because we simplify poorly on the AP test. Once more, plugging in the upper bound first. Notice it's the same function as that. Now that I've plugged in my upper bound, everywhere it says t, I'll multiply by the derivative of the upper bound, which is almost certainly 3, minus plugging in the lower bound for everywhere I see t, times the derivative of that lower bound. Now here's something I don't really want to simplify. I'm not sure I could fit it right here, to be honest, and that's a perfectly acceptable final answer. So we'll just move on. Now we're back to our classic 2t minus 3, except what we have here are some generic functions. Some functions we don't know more about, abstract functions. Doesn't matter, it's the same basic thing. Plugging in the top bound. Times the derivative of the top bound. What is the derivative of g? It's g prime. Minus. Plugging in the lower bound. Times the derivative of the lower bound, f prime. I don't think that scans so well. Just so you can all see what I'm writing, let's make it all purple. Okay. Last. Now this is a very special problem. This problem is more frequently a formulation of this question. A lot of students who cram the second fundamental theorem are trained to recognize when it says derivative of an integral. And that's what I'm telling you. You should recognize that. Whenever it says derivative of an integral, the second fundamental theorem is at play. We would use this whenever you see derivative of an integral. Only and then, too. But here I don't see that. And a lot of students, probably about 50% of the test takers, will skip this problem because they say, I don't know how to do it. Especially because I cannot integrate first here. You could integrate first and then take the derivative of all these other examples. Or at least, no, all of them. All of those other examples. However, here, because we have the 10th power, and I don't have a hook off of 2t, I cannot integrate this. So this is a problem where you need the second fundamental theorem, but also it's hard because it's not clear that you would use it. Well, if we just follow through and stay confident, what you might notice is that it tells you this crazy function definition where f of x is defined by plugging in here. So like f of 1 would be the integral from 0 to 3 of that function. F of 2 would be the integral from 0 to 12. And instead of that function, instead of talking about that, what it's asking me is about f prime. So I will take the derivative of both sides of my equation. I want to find f prime, so I'll take the derivative of that side, and that would equal the derivative of this side. And if we write it out carefully, now you would see that what it's asking you to do is the same thing as all of its brother problems. Now this question may or may not have been hard for you, because in this context it's the same. It's surrounded by a lot of its other problems, so you probably figured you might have to use this here. On the test, it's much more tricky than that. You'd have to identify that what they're asking you to do is the derivative of an integral. Plug in the top bound. Careful use of parentheses here would be rewarded. Notice there's 2 squares going on. Times the derivative of the top bound, which is just 6x, minus, and now I'll use this trick. Yes, I would plug in 0, but then I would also multiply by the derivative of 0. So minus 0. Just to show off exponent skills, just to be clear, we'd square the 3, we'd square the x squared. That would be an alternate answer. All right, I hope you were able to follow all of that. If you can't, feel free to rewind the video. Feel free to come see me. Good problem sets to do now. Problems 1 through 8 on page 110. Good luck, have fun, and I will talk to you later. Bye for now.